Hello. Today I'll be going through Griffiths Problem 2.9. Suppose the electric field in some region is found to be E equals kr cubed r hat in spherical coordinates. A, find the charge density rho, and B, find a total charge contained in a sphere of radius r centered at the origin. Okay, so when you're asked to find the charge density from your electric field, the best thing you can do is to use your divergence formula, because we can say that our divergence of the electric field is equal to our I believe it's rho divided by epsilon naught. So if we use that, let me just, it's rho over epsilon naught. Yes. So, and we want to find this guy over here. So before we start, we want to, remember we're in spherical coordinates. So in spherical coordinates, this would be equal to 1 over r times partial derivative with respect to r of r. No, this is not going to fit up here, will it? Then we have plus 1 over r sine theta d over d theta of a theta sine theta, and then plus 1 over r sine theta times d of a theta over d theta, or phi, if you want to be fancy. But before we go even any further, let's take a look back at our equation here for our electric field. You will recognize that we do not have any component for theta or for phi, so really wouldn't make much sense to do a dot product with that derivative, because there's no component to do it with. So we really only care about this guy, right? Makes sense? So we can go ahead and just do our dot product with that. So we have 1 over r times the partial derivative with respect to r. Don't forget that r inside. And honestly, don't memorize this. Write it on your cheat sheet or whatever you use when you're doing your problems, because that would just be a waste of time. So you have your r to the fourth. Wait a second. Something is a little off. You should actually read your cheat sheet correctly and put the right numbers in. And not put it there. Okay, so that is the correct formula for your r component. Don't forget that, like me. So you have 1 over r squared times a partial derivative with respect to r of r squared times, so ar is our r hat component. So I'm going to put k r cubed in here. So we have 1 over r squared times the partial derivative with respect to r of k r to the fifth. So this is a pretty straightforward derivative. You just have 1 over r squared times 5 k r to the fourth. And if you simplify this, it is equal to 5k r squared. So we can say that our divergence, so we said our divergence is equal to 5k r squared, but we're looking for our charge density. So remember, this is equal to rho over epsilon naught. So that means that our charge density is equal to 5k r squared epsilon naught. And there we go. That is part A. Now for part B, the fun part. I think the first thing you should do here is draw out your shape. So let's draw out some, hi Kat. Let's draw out some shapes here. So we're in a sphere of radius r, so let's draw our sphere. And I'm gonna give it some fancy 3D. And I'm gonna give it a radius of r, right? And it's centered to origin. Don't really worry about that. It's not that important for the problem. 1 second. Okay, so the first thing you should do is you want to find a total charge contained. So if you remember, your flux is equal to the surface integral of E dot dA is equal to the total charge enclosed over epsilon naught. So what we can do with that is we can say, okay, so just to start, we want to find the total charge enclosed, but we want to solve this surface integral. So the first thing you can consider is that since we're doing this dot product here, we really only care about the radial component because for any of the other parts in our spherical coordinates, the dot product would make no contribution. So when we're saying E dot dA, it's dot dA is really in the direction of the electric field. And since we have a sphere, remember that the electric field is radiating out of the center of the sphere. So this is the direction of our n hat, which is, you can also think of it as like E dot n hat, not that, E dot n hat ds. This is our n hat. So that's really the only component we care about. The other components of the electric, of our E, we don't actually consider. So keeping that in mind, we can actually do here is we can say that our flux is equal to simply the absolute value of E dA. And we're just going to remember, just use that n hat component, is Oof, I don't like, what the heck? Okay, that's weird. Hopefully I can exit this stupid mode. Okay, there we go. Right, so we're saying this is actually equal to, really, it's just, since the electric field is no longer dot product, we can actually pull it out. So we can say that's E times dA. See if this conversion makes sense to you, because we're no longer doing a dot product here, so it's just times, so we can pull it out since the surface integral is not with respect to anything inside the electric field. It's just a constant to it, because we took care of that dot product. So right now we can plug back in what our electric field is from up here. So we can say K R cubed, and remember I'm taking the absolute value, so I'm not getting that R hat in there because of what I said before. So we just have it times the surface integral dA, and that is equal to KR cubed times, so we're doing the surface integral of a sphere, so we just take the surface area of a sphere, and if you remember, that is 4 pi r squared. So we have 4k pi r to the fifth, right? So we're almost there. And we can say this is equal to our Q enclosed over epsilon naught. So remember, we want Q enclosed, so don't forget this part. We actually can say here that Q enclosed is equal to 4k pi r to the fifth times epsilon naught. And voila. But there is another way we can solve this problem too, and that is by saying that, let's put a little divider here between these parts. That is that we can say that our change in charge is equal to our charge density times a change in volume, right? Because that's really what our charge is. It's our charge density times our volume. So if we want to find our charge, and this is the same thing as Q enclosed. It's I'm just not writing Q enclosed. I'm just writing Q. We're saying it's equal to the volume integral of rho dV. So I really don't like when, some of these, if you've seen some solution manuals online that kind of go through example problems, they just kind of just say, oh, here's the integral of restricted volume. They don't actually write out the integral. I don't think that's really helpful, so I'm going to actually write out the full integral here. So we have 3 integrals of our charge density, which we found up there. So it's 5k r squared epsilon naught times r squared sine theta d rho d phi. And then let's set up our bounds for each of these integrals. I think I'm missing a dr. So we have 0 to r, 0 to pi, and 0 to 2 pi. This integral takes up a lot of space, but really, if you can see how it's written out, it's pretty straightforward calculus. You will get the same answer, obviously, from your other one since you're solving for the same thing. So, you know, if you do it wrong, it's pretty easy to check your work. So I'm just going to leave it as Q equals 4k pi r to the 5th epsilon naught. So see if you can run through that, get the same answer. If not, then you probably did something wrong with your integration. But yeah, that's it. Thanks for watching.